Now, gases are interesting, uh, uh, state of matter. So you can compress them. No, you know, uh, no other states of matter does that, which makes it like very useful in terms of being able to do some work. Uh, One of the interesting thing about gases is that they exert pressure, and they exert pressure in all directions. If you keep a gas in a container, it will give pressure upward, downward. Now, it doesn't happen in any other states of matter, right? So if you keep an object, it always exerts pressure towards the center of the earth due to the pull of gravity, but not for gases. So how can gases exert pressure then? They have to exert some force, but the gases are flying around in every directions. So how does gases exert pressure? To explain this behavior of gas, we have this kinetic molecular theory. So we are starting this chapter with the understanding of the kinetic molecular theory, the behavior of gas. Now, it makes some simple assumptions, and based on these assumptions, they build up a mathematical model that could explain the behavior of gases. Now, we are not going to go into the mathematical model, but we are going to learn what kinetic molecular theory is and what are the assumptions there, important assumptions. Um, so when gases do not behave like this, we say they deviated from the ideal behavior. So the first assumption is a gas consists of small particles that move randomly with high velocities. Okay. So what that means is why they assume that? Because it's like a moving car can exert pressure, right? So if the object is moving, then and if it hit onto the wall, it can exert pressure. So that is how gases are generating pressure by the random motion. Okay. The second assumption is that attractive forces between the particles of a gas are usually small. Now that was assumed to make the mathematical model simple. If there's only one force, okay, you have to do just one equation to solve it. But if they are attracting one another, there's a network of forces. So the initial mathematical model, so this is a model, right? So this model was simplified as much as possible. And one of the simplification is that attractive forces of the gas molecules are small and we can neglect it. And oftentimes we cannot. If the gas molecules, we now know polarity. Okay, if the gas is too polar, the molecules are going to attract one another like water vapor. Okay, and definitely this is not going to hold good under those conditions. Okay. Number three, the actual volume occupied by the gas molecule is extremely small compared to the volume of the container. Now, this is assume that the gas molecules are so small and there's a lot of space in between the gas molecules. And so the actual volume occupied by the gas molecules are almost negligible compared to the volume of the container. So you can basically consider the volume of the container as the total volume available to the gas molecules to move around. Again, that simplifies because if I know the volume of the gas container, I use that as the volume. Otherwise, we need to subtract, the volume of the gas molecules and things like that. More complicated math. Now, we do that more complicated math when required, but not under normal circumstance. Okay, so these are all, important assumptions made in the kinetic molecular theory. Now, you'll get questions from here. Okay, there's assumptions of the kinetic molecular theory. So, number 4, gas particles are in constant motion, moving rapidly in straight path. So that has to do. So this assumption is that as long, so they, so the, if they are not prevented by somebody, okay, they'll be moving in a straight line, and that way we can apply Newton's laws of motion and things like that. So again, that's to make the math a little bit more simple, and we can utilize the existing equations that we have in physics. Number 5, you know, this is another very important assumption. The average kinetic energy of the gas molecule is proportional to Kelvin temperature. Okay, so it's directly so if the temperature increases, the kinetic energy. Now, what is kinetic energy? Kinetic energy is the energy due to motion. So greater the velocity, greater the kinetic energy. So if you increase the Kelvin temperature, if the kinetic energy has to increase, that means the velocity, the speed of the gas molecules will increase. Okay, they're going to move faster and faster. So when you talk about a gas, we describe it in terms of four properties or parameters. Okay, pressure, volume, temperature, and amount of gas, and they are interrelated. So if I just tell you volume and do not tell you what pressure it is at, it means nothing, because I can apply greater pressure and reduce the volume, and then whatever I told you is wrong. So when you describe a gas, then you have to describe it in terms of all these four properties. Now, pressure, volume already know, okay, what volume means. Pressure is a kind of a new concept. So pressure is defined as force per unit area in physics, okay. So in order to have pressure, you know, there must be a force, and that force is coming from the the random motion of the gas molecules, and they're bombarding onto the wall, and that is where there's genetic force, when they bombard onto the wall of the container. Okay, and the units of pressure, and these are some of the common units that we use: atmosphere, ATM. So ATM is the most important one, and you can relate everything with ATM. Millimeter of mercury, we'll see what millimeter of mercury means. Now, if you have millimeter, you can always convert to centimeter and inches. Okay. And then there's the important one is the torr. So torr is nothing but millimeter of mercury. So you can replace millimeter of mercury with torr, same thing. And PSI, pound per square inch, is what we usually use commercially, like a tire pressure. Okay. And there are conversion factors, so you can convert from one unit to the other. Okay, and those conversion factors we need to know, and out of that, as I said, the most important one is the most important one is the ATM, atmosphere, ATM, 1 atmospheric pressure. Now, when I say 1 atmospheric pressure, that means is the average atmospheric pressure that you get at sea level. Okay, and it's taken. It is a constant. It has a definite value, 760 millimeter of mercury. So volume, you can think of any volume units. Okay, these are the common ones: liter, milliliter. Now, temperature. So temperature, as you see in the kinetic molecular theory, that the energy is related to Kelvin temperature. So all gas calculations must be done in Kelvin scale, and that is something that you must not forget. Okay, and the amount of gas, and we know that. So if you are basically filling up a balloon, if you put more air, or a tire, you put more air, you get more pressure. So in gas calculations, you need to take into account the amount of the gas, and the amount of gas is calculated, measured in moles. That means number of particles, number of gas molecules, not how many grams. Okay, how many gas molecules are there? So we state the gas amount of gas in moles. Now each of them are interrelated, each of these parameters, and these interrelations generate the laws that we'll see. So pressure and volume was studied by Boyle, Robert Boyle, and it's called the Boyle's law. Okay, volume and temperature studied by Charles, and it's called Charles' law. Similarly, there's a volume and amount of gas that was studied by Avogadro, and it's called Avogadro's law. Okay. So these are the, this is the summary of what I just said, and these are the units. Okay. Now, as I said, pressure is force per unit area. Okay. So that means the pressure exerted by the gases in the atmosphere is equal to the downward pressure of a mercury column in a closed glass tube. Now, what happens is, uh, and you can do that with water. So if you fill up a tube and invert that into a trough of water like this, the atmosphere is exerting pressure. Okay, on the outside is this blue line. So and it balances the pressure of this liquid column. Now for water, this liquid column is like 10.4 meter. Okay. Now mercury is very heavy. So if you take mercury, that liquid column basically is 760 millimeter of mercury. And that balances the atmospheric pressure. Now, if the atmospheric pressure decreases, the mercury column will decrease. So basically, we can have this column, this length of mercury column as a unit. And that is 1 atm, 760 millimeter of mercury. So Hg is mercury. Okay, so that is how we write millimeter of mercury, 760 millimeter. Then that is equal to 1 atm. So this millimeter of mercury is also called torr. So 760 is torr. Okay. Now the SI unit, the physicists use the force by area formula. So in there, the force has a unit of Newton, and the area is in meter square. So Newton per meter square. So that's called Pascal. So physicists use that more often. And in Pascal, 1 atm is equal to 101.325 kilopascal. Okay, so and the pound per square inch that is used for tire pressure is 14.7 pound per square inch is equal to 1 atm. So you have all these conversion factors here. Now you have to remember, this one. 1 atm equal to 760 millimeter of mercury. Rest are kind of related. Okay, so if you get millimeter, you can get centimeter, you can get inches. So don't really need to memorize it, but you need to memorize this one, this pound per square inch. Okay, 14.7 pound per square inch and 101.325 kilopascals. Now we can use this to convert between the units. Like here we have a simple calculus. A sample of neon gas has a pressure of 0.5 atm. Calculate the pressure in millimeter of mercury. Now you can see all these conversion factors are same that we did in a measurement. So when I give you the question like convert millimeter to kilometer, you have to show the conversion factor exactly like the way it is done. Okay, cancel the units. Okay. So everything is done the same way. So the whatever we learned in the measurement chapter, now we are using it here. This is a conversion factor. ATM cancels out, and you get 380 millimeter of mercury. Okay, an oxygen tank contains oxygen at a pressure of 2 atm. What is the pressure of the tank in terms of the following unit? So this is another question. In torr in millimeter of mercury. So this is already in atm, and just get the millimeter of mercury, that means multiply by 760. That's very simple, right? Yes. 760 multiplied by 2. And millimeter of mercury and torr are the same thing. Okay. Now, this is how we convert pressure. Okay. Now, Robert Boyle, performed. Now, we all know that, right? So if you apply pressure, volume decreases. Robert Boyle did more scientifically, like studied it, like get the data, did some plots, and he got some mathematical equations out of that. So this is the first time probably, scientifically studied. Robert Boyle started that. So whatever you are doing has to be mathematically, you can write it mathematically. So Robert Boyle says that the volume of a sample of gas changes inversely with the pressure. as long as the temperature and amount of gas remain constant. That means inversely means directly means if it changes directly, then we say that if you double x, y doubles. Inversely means if you double x, y gets halved. This is the inverse function. And we write it like this: V is proportional to 1 by P. Okay. And T and N is the number of moles, T is the temperature. So those two parameters, you cannot vary all four. So when you are varying two, you have to make the other two as constant. Okay. So then PV equal to constant. What that means is no matter how much pressure and volume you change, the product is always constant. That means if I let's say initially started at pressure P1, volume V1, and then I change to pressure P2 and the volume change to V2. So no matter how many changes I make, always pressure multiplied by volume will remain constant. So we can write this as P1 V1 equal to P2 V2. Mm-hmm. And what it allows us to do, so if I know any three parameters, I can figure out the rest. Mm-hmm. So with this equation, we can basically predict the volume under new pressure. We can actually give the number, quantify. Okay, we know that if I increase the pressure, volume will decrease, but now we can say by how much. Okay, so these are the guides for using the gas laws. So when you are, so basically what you are saying is that P1 V1 equal to P2 V2. Now, depending on what I need, I can always rearrange the equation. Okay. So to just rearrange the equation. So let's say if I need V2, I can write V2 equal to P2 by P1. So you just divide both sides. Okay, you just divide both sides by P1. So basically, what I'm doing is if I need to isolate P2, V2, I did something wrong. So V2 equal to, oh, let's see. I wrote everything opposite. So if you want to isolate B2, you have to divide both sides by P2. So that way, it becomes easier. Okay, so if you divide by P2, this P2 and P2 cancels out. So you have P1 by P2 into P1. Now you substitute. Now you can see this P1 by P2. That means your unit, pressure unit can be anything. It is going to cancel out as long they're same. You do not need to convert like ATM or anything. As long they're same, you are okay. Okay. So if you look at problem 8.3, calculating the volume when pressure changes, the gauge on a 12-liter tank, compressed oxygen is 3,800 millimeter mercury. How many liter would the same gas occupy at a pressure of 0.75 atm? So we are basically, so always write down what you have, right? Like here, the small table. Okay. So always create the small table that you see here. So P1 is 3,800 millimeter of mercury, and P2 is 570 millimeter of mercury. Now, notable thing is this is a millimeter of mercury, and this is an ATM. You cannot have different units. You have to have one unit. It can be anything. Okay, so it can be anything. So either use all ATM or use all millimeter of Hg. Okay, and then when you do the math, simple math, and the gas equations are very simple. Okay, just don't make careless mistake in rearrangement and things like that. And that is what usually happens. Well, like I made a mistake here. Okay, so always double check. Okay, And if you follow the units, you will easily catch it. Okay. So the correct answer is 80 liter. So if I change the pressure from 5 atm to 0.75 atm, the volume will increase from 12 liter and will become 80 liter. So 80 dot, two significant figure. Okay. So this is the relationship between pressure and volume. Now, Robert Charles, not Robert Charles, I think, what's his first name? Jacques Charles or something. Okay. Robert Boyle. So Charles, he studied volume, a relationship of volume with temperature. Okay. And what he found, he stated as a law, Charles' law, it says that the volume of a sample of gas changes directly with Kelvin temperature. So this is very important that this is in Kelvin. Please don't forget this one, okay? So and students do forget. So that's why I keep repeating that. Don't forget. Okay. So volume proportional to temperature, and when you are changing the volume and temperature, pressure and moles amount of gas remain constant. What that means is V by T equal to constant, or V2 by T2, V1 by T1 equal to V2 by T2. So this is this is the equation that we'll be using for our calculation. So if you look at this problem, so always, whenever you get a big problem like this, prepare the small table. Okay, get the numbers that you need. And then you don't have to look back. Okay. So the problem says that calculating the volume when temperature changes. A sample of argon gas has a volume of 5.4 liter and temperature 15 degrees centigrade. So when you read a question like this, mark out the key data and write it down as a table. Okay. So my key data is 15 degree. Okay, 5.4 liter. and then this is the question, what is the volume? What is the volume if the temperature increased to 42? Now, the reason I'm saying that you need to be careful because there's T1, there's T2, you need to know which one is where. Otherwise, it's a very common mistake to switch the T1 for T2. Okay. So you write down, the temperature, so this is the Kelvin temperatures. This is what we're going to use. We cannot use degree centigrade. And this is the question. Okay. So we are starting with this equation, this one. Now from here, if you rearrange, you get here. Now how? Well, isolate T2. Isolate B2. So this is what we are trying to do. We are trying to isolate B2. Okay. So how can I isolate B2? If I multiply both sides by T2. So just multiply by T2 both sides, right? So if you multiply both sides by T2, then your T2 and T2 cancels out. So what you're left with is this, that V2 equal to V1 multiplied by T2 by T1. Again, temperature will cancel out and the volume will have the same unit as your V2. Okay. So if you substitute, is 5.91 liter. So pretty simple math, but again, this rearrangement, conversion to Kelvin, this is where most of the mistakes come, careless mistakes. Okay. So relation between temperature and pressure, this is GayLussac's law. So just like the previous one, so it's P directly proportional to T, to P by T equal to constant. So P1 by T1 equal to P2 by T2. And then you can use that to do a math like this. Okay. So calculating the pressure when the temperature changes. So these are simple problems, okay? Now, if you combine these gas laws, so how do you combine it? So this is the theory of joint variation. So we have volume proportional to 1 by P, right? And we have volume proportional to T. So if you put them together, if you write them together, the volume is proportional to 1 by P multiplied by T. So this is called the joint variation. And so that means PV by T, or let's say like P is equal to some constant K. Whenever this proportionality, you can write a constant, okay, into T by P. Okay, so if we rearrange PV by T, so K is a constant, okay, PV by T is equal to constant. So this is nothing but you join these two laws. Okay. and then we can write P1 V1 by T1 equal to P2 V2 by T2. Now, if you know this, you can forget the previous equations. Why? Because see, in this equation, if I say that your temperature is constant, okay, like N is constant for all, if the temperature is constant, T1 equal to T2. So if T1 equal to T2, that means we can cancel. Why is it not writing? So your T1 and T2 is going to cancel out. So what you're left is P1, V1 equal to P2, V2. And that's Boyle's law. If pressure is constant, that means P1 is equal to P2. So V1 by T1 equal to P2 by T2, which is Charle's law. And similarly, volume is constant, you get GayLussac's law. So this is basically the only equation that you need to know. And all the other equations are in that equation. You can always figure them out. Okay. Now we have to be very careful with writing out the parameters. Okay. So when you write the parameters, you can write it like this, like the way they did, or you can write it like, at the very top, you can have, so give yourself some space. Okay. P1, V1, T1, that's for state 1, and then P2, V2, T2. So write this down.
P1.
And you have a T2. Okay. Now here it says that a 25 milliliter bubble. So B1 is 25 milliliter. Okay. Is released from a diverse air tank to a pressure of 4 atm. The pressure of 4 point now is 4.00 atm. So keep to the secret.
Pressure P1.
Okay, and temperature is 11 degrees centigrade.
4 point.
So 11 degrees centigrade plus 273, right?
Yes.
And that is equal to 284 Kelvin. Okay, you show the math here. 11 plus 273. Okay, so I'm writing with one finger. So that's why I'm writing on my iPad. So that's why it's taking time. So now your P2, what is the volume of the gas bubble in milliliter? So B2 in milliliter.
2
Was that unknown?
And P2, where the so when it reaches the ocean surface, where the pressure is 1 atm to 1.00 atm,
1.00.
atm, and temperature 18 degrees centigrade.
Plus 273, 291 Kelvin.
18 degrees centigrade. And so that is equal to 291, right?
Yes.
291 Kelvin. So I need to isolate V2. Okay. So your P1, so you see that this is your V2, right?
Yes.
And if I need to isolate V2, I need to cancel out T2, right?
And P2.
I need to cancel out P2. So then your T2 and T2 is going to cancel out. Your P2 and P2 is going to cancel out. Now I need to write the same thing on the other side. So that means I need to write P2 by P2.
Oh. Okay, T2.
So that is what, and you just substitute. So your V2 equal to P1 by P2 multiplied by T2 by T1 multiplied by P1. I just rearrange it a little bit. Just make it look nice, that's it. And I know that if my pressure are in the same unit, they're going to cancel out. So your pressure is P1 4.00 atm. And this is 1.00 atm. So your ATM and ATM is going to cancel out. You know that. And then you have T2. So T2 220 Kelvin. So you have to write it very systematic, otherwise very easy to get it wrong, okay? Because there's so many variables. And 284, right?
So you divide and multiply?
No, I mean I'm just see where is T1?
Oh.
You just don't don't challenge your brain too much on asking divide or multiply. Just follow the units, place it, and just substitute. So T1 is at the denominator, right? So I'll put it in the denominator. And then you have V1. So our V1 is 25 milliliter.
Okay.
So now you see milliliter is my unit. That's not cancelling. So that's what I need, right? So 4.00 divided by 1.00 multiplied by 291. 291 multiplied by multiplied by 25.
Milliliters.
Okay, and these are all in milliliter. And divided by 1.00.
All everything.
And you have 284.
Times 291.
Now you see 25 milliliter is too big. So your answer must be too significant here. This is another problem. Okay. So here, let's see. So a weather balloon is filled with 15 liters of helium at a temperature of 25 degrees centigrade. So this is your V1. Okay. This is your T1. at a pressure of 685 millimeter of mercury. So this is a P1. Okay, what is the pressure in millimeter of mercury? So P2. P2 is asked. So you are asked what is P2 in millimeter of mercury. Okay, that's the unit of the helium balloon in the upper atmosphere when the temperature is minus 35 degrees centigrade. Okay, T2. And the final volume P2 is 34.0 liter. So I have all the parameters. Okay, so again, do the table, and is saying that other parameters like the amount of helium is not changing. Okay, so you have to find out V2.
It.
So here it says a weather balloon with a volume of 44 liter is filled with 2.0 moles of helium. What is the final volume in liters if 3.0 moles of gases are added to give a total volume, total of 5.0 moles? So we have N2, so we have V1, we have N1, and we have, if 3.0 moles are added, see, if 3.0 moles are added, now they give you the total, but they may not give you the total. You have to make the total, okay? If they don't give you the total, then you have to, total it up. And so these are N2 here. And the rest are not changing. So B1 by N1 equal to B2 by N2. So you need to isolate. So you are asked here, the question is, what is the final volume? P2 is the question, okay? So you have to basically isolate.
Yeah.
You have to isolate V2. So that means you have to multiply by N2 on both sides. So N2 and N2 cancels out. So yeah, this is, then you just substitute. So that was a simple one, okay? And Avogadro's law is pretty simple. So it, it will not get any harder than that, okay? Now the next is molar volume. Now you saw that the volume kind of changes, right? If I increase the amount of gas, so many variables, so you need to fix something. So that fixed temperature pressure usually called the STP, okay? So STP, standard temperature pressure. So whenever you want to say something in STP, people know what you're talking about. So a standard, now you'll get this question, what is the standard temperature pressure? Okay. Standard pressure is 1 atm exact. Exact means no error. So do not attach a significant figure to them. And standard temperature is 0 degrees centigrade exact. So an STP, 1 mole of any gas occupies 22.4 liters. And this is called the molar volume. And that is fixed. That means I can use that as a conversion factor. If you look here, the molar volume conversion factor, so 1 mole of gas equal to 22.4 liter is a conversion factor. So I can go from moles to liter and liter to moles at STP. We can also do that in other temperatures, but we're not covering that part, okay, the gas equations. But we'll keep to STP for now. Okay. So what this means is that if I take 1 mole of helium, so if I take 1 mole of helium, 1 mole of oxygen, 1 mole of nitrogen, they'll occupy the same volume, 22.4 liter at STP. But if you look at their masses, they're different. So 1 mole of helium is 4.003 grams of helium. 1 mole of oxygen is 32 grams of oxygen. And 1 mole of nitrogen is 28.02 grams of nitrogen. So is the number of molecules that represent. That's same in all three of them. And then the volume will be constant and equal to 22.4 liter at STP. So these are the conversion factors we can use, and depending on what we need, we can go from one to the other. So here is a problem. So what is the volume in liter of 64 grams of oxygen? Now we cannot use it as grams, right? So we have to go from grams to moles,
Mm-hmm.
and then use molar volume to go to liters. So you have two conversion factors here.
What are the volume?
So, and these are the two conversion factors. So the molar conversion factor is 1 mole of oxygen is 32.00 grams. And how do you know that? From the periodic table. So you'll be provided with the periodic table during the exam. You don't need to memorize. Okay. So you can look up now oxygen is O2. There's another thing that you should be aware of. And so if you look in the periodic table, it says 16. But because it is O2, so it's 32 grams per mole. And then multiplied by the, molar volume conversion factor, you get 44.8 liters of oxygen. Okay. Now do this study check. Oh my God, it's done. Anyway, do this. So how many grams of nitrogen gas is in 5.6 liters of nitrogen
Yeah.
at STP? So now you are asked grams.
Mm-hmm.
And so you should go from liter of nitrogen. Okay, so volume of nitrogen, you want to go to mole of nitrogen. And from there, you want to go to grams of nitrogen at STP. So use the conversion factor here, use another conversion factor here. And follow the unit, okay? So unit must be in liter. So you're starting with liter and use conversion factor for, use unit for all conversion factors, okay? So liter of nitrogen should cancel out and mole of nitrogen remains. So that's your setup of the unit. And then mole of nitrogen should cancel out. And grams of nitrogen remains. Okay. So put the numbers and do it in the calculator.
I'm getting 7.0025.
Okay, so you have to convert that to 2 feet because 5.6 liter is too significant figure.
Okay.
Okay, so the next law that we will look at is the Dalton's law of partial pressure. This is again a very, very easy law. Okay, so it says that if you have a gas mixture, okay, that the total pressure equal to sum of the partial pressure of all the gases. Just simple addition. Okay, so that means total pressure P, the total pressure. So the partial pressure, and I'll define partial pressure. So if you have the partial pressure, let's say, you just add the partial pressure, and that's your simple equation there. Now, what is partial pressure? So if you have a gas mixture, if you isolate, say it's a gas mixture of A and B, if you isolate A and allow A to occupy the same volume as the container, as the mixture, so the pressure that it would exert is the partial pressure. Okay. So if you have the partial pressure, you just add the partial pressures and that is the total pressure. Now, the partial pressure can also be calculated as mole fraction multiplied by total pressure. That means if you look at air, so air is 80% nitrogen, okay, 80% nitrogen, 20%, 80% nitrogen and 20% of oxygen, okay. So that means and the total pressure is 1 atm. So 80% is, we can write 80% is uh, 0.20. Okay, that's a fraction. Sorry, 0.80. That's the fraction. Okay, and this is equal to 0.20. So, and the total pressure is 1 atm. Total pressure is 1 atm. Total pressure equal to 1 atm. That means the partial pressure of oxygen, P, we write it like this, partial pressure of nitrogen is equal to 0.8. That's the mole fraction, okay, multiplied by 1 atm. So this is equal to 0.8 atm. 80 atm. Similarly, for oxygen, the partial pressure of oxygen, if you do the same math here, the partial pressure of oxygen, you can do the same thing and you'll get 0.20 atm. Okay, 0.20 atm. So if you add up the partial pressure, if you add up this partial pressure, that is equal to total pressure. So if you add this up, you get what? 1 atm, which is the total pressure. So this is Dalton's law. So sum of partial pressure is equal to total pressure. Okay. Now we are going to use this in our lab. Okay. So we had experiment where we are going to use this for the lab. Now, so that means, so it has very simple problems. Okay. Simple kind of question. So let's say that at a depth of 200 feet underwater, a scuba diver breathes a gas mixture, okay, of oxygen and helium. So there's a mixture of gases there. That has a total pressure of 7 atm. That is our total P. Okay, so let's say PT, P total. If the partial pressure of oxygen, so PO2, okay, partial pressure of oxygen is 1140 millimeter of mercury. What is the partial pressure in atm of the helium? So the question is, what is that of helium?
In the breathing.
Okay, now, so this is atm and millimeter of mercury. Okay, so if you see, this is the equation that you're using, that P total, here it is. So P total equal to P oxygen plus P helium, right? And so we can say that P helium is equal to P total minus PO2. So the PO2 is given to us, okay, which is 1140 millimeter, but we cannot use it like that. So 1140 millimeter needs to be converted to atm, same unit, okay, and so 1.50 atm, and then you basically substitute. So 7.00 is the total, okay, minus 1.50 atm, which is the oxygen, and you get 5.50 atm. Okay, so simple problems. Now, so how can we apply this? So let's say that in the lab, you are collecting a gas, okay? So, so like usually, for many gas experiments, we do the reaction, okay? So let's say this is our reaction, and then we let the gas come out, and we collect the gas over water. So this is kind of a trap, okay? And you have water here, and we basically collect it by downward displacement of water. So you keep these bottles filled with water, okay, and the oxygen, whatever gas you are generating gets collected here. So, but because you are collecting it by downward displacement of water, this mixture will have the gas plus water vapor. So vapor of water. So there are two gases, okay, water vapor. So water vapor and your actual gas. So in order to do a calculations, now you are collecting it by downward displacement of water. That means the atmospheric pressure. That's the total pressure of the gas plus vapor. So in order to do a calculations, okay, you need to figure out what is the partial pressure of the gas itself by itself without the water vapor. So you subtract the value of the pressure of water vapor. Now you can get a standard chart. Okay, so you can look at the chart, look at the temperature, and you know what the vapor pressure would be at that temperature. Okay, so then you subtract the vapor pressure.
Mm. Oh, okay. Mm-hmm.
So water vapor is just like any other gas. So you just subtract the pressure of the water vapor at that temperature. Okay, and then you can use that whatever you are getting, the pressure from the dry gas, that is what you're going to use for your calculations. Because sometimes we calculate how many moles of gas is produced. Okay, and then you need the actual pressure value. So you subtract from the atmospheric pressure, the water vapor.
1 divided by 7 equals, okay, got it, 1 point of total. Subtract it from, oh.
Okay.
Mm.
So that's the end of a chapter. Yeah.
Okay. So then let's just
Okay, now what did you learn from this chapter? So many things, right? But again, it can be written as one equation. This is the second one. Only two equations. That's it.
oh, okay. That's gonna be our
Now,
for the
yeah,
week.
because see, this is one equation. As I said, this is the one equation P1, P equal to P1 plus P2, and you have to only know one other equation, and that's it. Uh, so if you know that P1 V1 by N1 T1 is equal to, write it 10 times, okay? And that's it for this chapter. These are only two equations, N2 T2. Now, as you saw, that if we say that uh, if N1 and T1 doesn't change, what you get? You cancel N1 and T, you just cover it up. Okay, you get P1 V1 equal to P2 V2. Boyle's law. If I say P1 and N1 doesn't change, then you get V1 by T1 equal to V2 by T2. If I say that uh, B2 and N2 doesn't, B and N doesn't change, then P1 by T1 equal to P2 by T2. If I say that only N1 doesn't change, then we have P1 by P1 V1 by T1 equal to P2 V2 by T2. So everything is there in one equation.
Mm.